Okay. So this is the set of all of the values that are achieved. Okay, so you have a whole bunch of numbers there, and I want to show that there's actually an absolute maximum. So I'm sure you've seen probably the pictures of this when you were in calculus, right? You have some function here, right? If my domain is like this, well, on that interval, there is no absolute maximum or minimum because you can't actually touch that open circle or that open circle. But as soon as your set is closed here, right? As soon as it's closed, now you fill in these points and you've got the absolute maximum and minimum achieved. Okay? So this is where we're going to actually use this part of it. Okay, so this is kind of continuing along from what we've already concluded, right? So since f of capital X is closed, right, it's going to contain its own supremum, right? The supremum of the set of f of x's where x is in capital X is an element of f of capital X. And this one right here is the maximum value. The supremum of all of those numbers. It has to actually be f of something. See, even if I go back to this again, if I go back to the open interval, right? The supremum of this set of values, it does exist. It's right here. This is the supremum of that set of values, but that supremum is not f of something because this point doesn't exist in my domain now. Right? But because the set is closed, this supremum is actually f of something. It's in the image of the function. Yeah, Alex?
Can't you argue that the supremum is a limit point?
Yep. Yeah, that's basically what you're doing. Yeah, the supremum is a limit point of the set f of capital X. And because f of capital X is closed, it contains all of its limit points. And so therefore it has to contain that supremum. Yeah. Okay. So I'll just maybe note that as well. This is a limit point of f of capital X. That's right.
So part of the definition of a supremum, it is a limit point?
Essentially, that's true because I can create a sequence of numbers that converges to this. If I call this alpha, right? I can create a sequence. So for all natural numbers n, this goes back to 350 basically. For all natural numbers n, there exists an xn in the domain such that the distance between f of xn and alpha is less than 1 over n. You can create a sequence that approaches alpha.
Okay.
If you couldn't do that, then alpha wouldn't be your supremum. You could actually make your upper bound smaller. So that's basically the reasoning. Okay. Okay, so I think we're good on that. Okay, maybe one more thing here, and then I think I'll probably just go ahead and stop. This is number 7. So here's number 7. Are these collections bases for a topology on R? And we're going to do a few examples, okay? So part A, script B is going to be the set of open intervals a plus 1, such that a is an integer. Oh, by the way, I forgot. For the minimum, you just have to use the infimum. Same reasoning. I just didn't write that one down. Just focusing on the maximum case there. Okay, so do we remember anything what this has to do with?
Yes, no.
Proposition 4.
Sorry, go ahead.
To check if it's a basis, we use proposition 4 in chapter 4, I think.
Right, I was just opening up to proposition 4 from chapter 3. This is a good one to remember. So if I give you a family of sets, this is a family of open intervals, and I ask you, is it a basis for a topology? There's two things that have to be true. Do you remember what they are? They were written as I prime and I double I prime. So
you have to cover the whole set.
right, so the first one is that X is a union. So X in this case is R, is a union of members of B. Okay, and then the second, what was the second property?
When we take the intersection of any two members in B, that can be expressed as union of a member in B.
Exactly. So the intersection of two members of B is expressible. How did I phrase it here? Well, I just said is a union of members of B. So this is proposition 4 back in chapter 3. So it's been a little while, but that's what we're really asking you about here. So I'm glad you guys picked up on it right away. I thought I would pick some random topic from like 2 months ago and see if anybody remembers it. You guys even remember the proposition number. Yeah, this is the one. You don't have to remember the numbers, of course, for the exam, but it's nice if you do, I guess. So you can see right away that because A is restricted to be integers here, that the unions of all of these misses the integers actually, because these are open, right? So I prime fails. So I prime fails here. So the answer is no for this example. It's no on that one, okay? Let's try another one of the same kind of thing here. Where did it go? Oh, here it is. Let's try this one, part B. Let's take script B to be the set of closed on A and then A plus 1 such that A is an element of Z.
Yeah.
Okay, what do you think? Is the union, is the whole real number line going to be a union of those guys?
Yes.
Absolutely. Okay, because you just union all of these together for each integer, and you'll get the whole real numbers. So this is yes, since R is equal to the union of the interval from A to A plus 1. It's half open this time, where A is an integer. So that's just really what we're saying. What about the second part of it?
Empty union.
If you intersect two of those together, what are you going to get? As long as they're two different intervals, you intersect them, you're going to get the empty set, right? So A plus 1 intersected with B to B plus 1. If we intersect two things like that, it's going to be empty. Now the empty set counts as an empty union of members of B. Empty union just means you didn't union anything, so you have nothing, right? Unless A equals B. And of course, if A equals B, then of course that intersection is itself one of the sets in B, because it's where you started from. So that's also true, so the answer here is yes. Okay, I'll give you one more. let's take, and be careful now. So guys, if this was let's say I had this as my topology. Now your open sets are looking like this. You have to be very careful because this is not your intuition working at this point. So now in this topological space, for example, the interval from 3 to 5 will be an open set. So it's always relative to the topology. And so, I could do that. Like I could give you kind of a weird topology like this and then start asking you about frontiers and closures and all this stuff and really test the definitions. So practice that a little bit. Take some of these examples and see what you can do with them. The third one I want to do is this one. The script B is the set of the closed interval from A to A plus 2, where A is an integer. So we have our proposition 4. Is the whole real line going to be a union of those?
Yes.
Yes.
Okay, so I prime is yes. R is equal to the union of the closed interval from A to A plus 2, where A is in the integers. Okay. What about the second part, the double I prime?
Yes.
If I intersect two of these together, will I get a union of things like that?
No. Take consecutive.
Give me an example.
A is 1 and A is 2. You get a.
So 1 to 3,
Yeah.
that's in the basis. I intersect that with 2 to 4.
Yeah.
That's in the basis. We end up getting the interval 2 to 3, which is not in the basis, and it's not a union of things in the basis, because this is only an interval of length 1. Right?
Yes.
Okay, so this is not in script B, so no, this one would fail, and that just means we don't have a basis here.
So that means if we're intersecting the two intervals and we get, even if it looks so close, so it looks so similar to the memory.
It looks like the same form, but it has to have a length 2.
If it has different lengths, then it still counts.
It doesn't work. Yeah,
Yes.
that's
Oh,
right.
Okay.
That's right.
I think I understood this one wrong before. So
Did you see it before?
I mean, like the
Oh,
no,
just
I mean like
when you were first
the
thinking?
using the theorem itself. I mean, like
Mhm.
the second part, I was assuming like if it has the same shape,
Oh,
then I
no, it
I
has to
didn't need
actually
look
be.
at this.
It has to actually
What's
be a
inside.
union of members of B, so it has to look like exactly that right
Exactly the
form.
same. Okay.
Yeah, so that's a little tricky to make that work. Yeah. Let me just see if there's anything else I wanted to do. Maybe not. I did the Cantor set. Is the Cantor set dense in 0-1?
I think so.
Remember this is the example we did earlier. I just want to go back to it again. So take 0-1, you remove the middle 1/3. So now you go from 1/3 to 2/3. And then you remove the middle 1/3 of both of those. You get 1/9 here and what is it?
Yeah.
8/9? No. 2/9. And then do the same thing here. This is 7/9, 8/9. You keep going like that. You take the intersection of all those. Is that going to be dense? So let's remember what dense means. Dense means a closure is the whole set. So is this dense in the closed interval 0-1?
No.
Definitely not. Because actually the Cantor set itself is, we already said it's closed. So it is its own closure. If it's its own closure, then it's definitely not, the closure is not the whole space. So it's not dense. Is it somewhere dense?
Yes.
Yes.
So somewhere dense means that if you take the closure of the set and then the interior of that, It's
It's
not empty, right? So is that true?
So the closure of A is
So A is the Cantor set.
so the
Stuff is equal.
The closure of that is itself, right? What's the interior of the Cantor set? Which points in the Cantor set can you draw a little neighborhood around
The
that stays
open
inside
sets
the...
are
just
So can I pick a point, like there's a point in the Cantor set, right? Will I be able to put a neighborhood around it and that whole entire space will stay in the Cantor set? Keep in mind, you're doing this chopping up the interval infinitely long. You keep dividing it into thirds.
It's empty.
It is empty. Yeah, there's nothing in the interior. This set is nowhere dense. The Cantor set is amazing. It's nowhere dense. It's compact. It's closed. It's bounded. It's nowhere dense.
Uncountable.
And it's still uncountable. It's just as big as the closed interval 0, 1 that you started with. And yet somehow it's not anywhere dense at all. Nowhere dense. Yeah, so actually, so this one, for the Cantor set, the closure of the Cantor set is empty. Okay, I just thought of that because I hadn't reviewed denseness. So make sure you review what dense means, somewhere dense, nowhere dense. Should be pretty good. Everybody's good with homeomorphisms and separation axes. We just studied for a midterm like 2 weeks ago. So I'm hoping between that and then the take-home test has lots of stuff with the Cartesian product on it and compactness on it. So that should be helping you, I hope, helping you review for that part of the test as well. So just again to remind you, I'm going to be going to do another review at 4 o'clock with my other class. I'll be here for a few minutes now if anybody wants to talk. Otherwise, I'll be back this evening after my other review. And I'll be here tonight as well. I'll be here tomorrow. I'll be here the next day, and the next day, and the next day. So see you guys as much as we need to. We'll get things
for
figured
one
out.
season, basically.
Is this good?
Yeah, we do.
Helpful?
Yeah, we did.